Welcome back all of you. In the last two classes rather, we discussed more about pulse phase and receiver phase, and we understood what happens if you apply the pulse along x axis, minus x axis, and plus y axis, minus y axis, how the magnetization can be made to rotate in different directions, whether clockwise or anti-clockwise. And also we understood what happens if I have a when I tilt the magnetization from thermal equilibrium to x axis or y axis. Depending upon where I keep the receiver, whether I keep the receiver along plus axis, whether the magnetization is along x axis only, then we get absorption mode signal and the imaginary part will be dispersive. So what happens if the receiver position is changed in different axes, whether what type of signal we are going to get, whether you get absorptive or dispersive. This is what we understood. Okay, and at the same time, what happens if there are two receiver channels to detect the signal? If there is an imbalance between these two, then what we can do is there is a phase error. For that I showed you we can do different type of experiments, 4 experiments. Each time we have pulse phase and receiver phase is adjusted in such a way. We collect the signal, the real and imaginary parts are changed accordingly. Every time we change the receiver and change the pulse phase and coord the signal, and you will see that there is a perfect balance between this real FID and imaginary FID. The phase error will not come into the picture. This is what we understood also. So with that, now what we are going to do today, we will discuss about the evolution of the magnetization. So far we have been applying pulses and everything. How the magnetization evolves, this is very important to understand the product operators. It is very important to design your sequences. Let us see how the magnetization evolves in different pulse sequences. Okay. Now, motion of the magnetization vector in a rotating frame is called an evolution. The rotating frame we discussed long back in the previous course. What is a rotating frame, everything, we will not go into the detail. But yes, please remember one thing, the evolution is nothing but the rotation of the magnetization. That is what the thing we must understand. Now consider a situation, we have magnetization, bring the magnetization, equilibrium magnetization to y axis. The magnetization, what will happen to the magnetization? It starts precessing in the clockwise direction in the xy plane. The precision rate is proportional to the offset from the center of the spectrum. This is very important. In the rotating frame, let us say I have a spectral width here, this is my center, this is my offset, and if the signal is exactly here, that is a different question. The signal is somewhere here, this is what is called offset. We call it as delta nu or delta omega. This is the offset, and from the center of the spectrum. And how far it is, this will define your rate of precision, how fast the magnetization is precessing. If it is here, there is one speed of rotation. If it is here, the rotation is different. So the speed of how the magnetization is rotating is understood by how far it is from the center of the spectrum. Okay, this is now we will do one thing. This is what the important point. Now you have brought the magnetization to y axis and receiver is along x axis. That is the important point. Now what is going to happen? The mx component, first part. Now I am allowing you to rotate in the xy plane. So far we are only collecting the signal and I was receiver phase and other things, we did not discuss about the rotation. We simply understood what happens to the signal at different phases. Now we will see how the magnetization rotates in the xy plane. In the receiver is along x axis. The mx component will precise like this. As soon as the signal comes here, mx component, it will become maximum signal. Maximum is the thermal equilibrium magnetization M0. Then it will go to other axis minus depending upon the direction of precision, it goes to y axis, you will have a 0 signal. Then goes further, it rotates like this, it comes to minus x, you will have minus m0. Magnetization will be negative because your receiver is here, and then goes further, it will become 0. Very interesting. You see what is going to happen? Magnetization 0, m0 here maximum, 0 minus m0, and it will become 0. It goes to one full rotation in the xy plane. This is what happens to the cosine part. What happened to the sine part? It is very easily you can extrapolate this thing. Sine part and cosine part is differing by 90 degree. So it starts with 0 then. Sine part starts with 0, goes to m0, start here when you do have the receiver here, the sine part is 0, then goes to m0, m0, 0 and minus m0. So exactly it starts rotating. Cosine starts rotating like this, sine also starts rotating like that, but there is a phase difference of 90 degree between these two. Both the magnetization components are rotating. Okay. Now Fourier transformation of the mx and my components we can do. What will happen if I do the Fourier transformation of mx and my components? You will get cosine part and the sine part, both we will get. That means you will get absorptive signal. I told you already, we discussed in the previous class, absorptive and dispersive signal both we get. Now remember, receiver is along x axis. What we do? When you do the receiver is along x axis, you get absorptive signal. That is what we said. mx is along x axis. Immediately as soon as you apply 90 degree pulse, your received is along x axis. So real part of the signal is absorptive and imaginary part is dispersive. That is perfect. Now what happens if the FID is collected after certain time delay? Now I am allowing it to rotate in the xy plane. Magnetization component starts moving, mx and my. How it moves we already understood, m0, 0, minus m0 and 0 for a cosine. Sine is 90 degree out of phase like that. Okay, so immediately after the 90 degree, instead of collecting the signal here, where you get absorptive part, now I am allowing it to rotate. Magnetization start precessing we call. Let us say what will happen if start precessing. And now allow the magnetization to evolve my component for a time t. And now let us say a component mx has moved here, my has moved here. They are moved by some distance. It is not exactly a 90 degree or this thing. See, this has moved from here to here, this has moved from here to here. They are not outside. Between them they may be out of phase by 90 degree, but they are not. Receiver is here. As far as the receiver is concerned, they are moved by some distance. So during the delay, magnetization has evolved by certain amount. This is what is called evolution. Magnetization during this delay has evolved. So collection of FID will be at a different point. The free induction decay is not collected at the right point. We collect at a different point. Okay. Now what do you say? The magnetization is evolved under chemical shift, because this is what is going to happen. Apply pulse, bring the magnetization, leave it like that. Magnetization start evolving, and this is evolution is called a chemical shift evolution. It evolves under chemical shift. I am now talking about chemical shift. We will bring in coupling later. Okay. If the magnetization evolved for the duration t such that mx and my component move exactly by 90 degree. Understand the point. They have moved exactly by 90 degree. So what will happen? ms component in the coil would be shifted by 90 degree. The real part will appear like dispersive, and my component is also phase shifted by 90 degree and will be absorptive. Now both the components of magnetization have moved by itself. So chemical shift evolution has taken place. This is called chemical shift evolution. They moved by 90 degrees. Now mx is here, mx has already moved here, my is moved here, and receiver is still here. So what is going to happen? The real part will be dispersive and imaginary part will be absorptive. This is an important point. Okay. Now if the magnetization evolved for the duration t such that mx and my component move by 90 degree, 180 degree, not 90, 180 degree, then what will happen? mx component will be phase shifted by 180 degree, and that will become negative absorption, because from here it started moving like this and it has come to this axis. Receiver is here. So instead of plus x, you are going to have the signal in the minus x axis. So it means there is a phase shift by 180 degree. Phase shift of 180 degree, what will happen? The absorptive component, positive absorptive became negative absorptive. So that is what is going to happen. Similarly, real component becomes negative dispersive signal. My become negative dispersive, and this is what happens when move the magnetization mx from here it has moved to here, my from here to here it has moved. So the positive part, real part is negative absorption, and imaginary part is negative dispersive. Now I am allowing the magnetization to move, components of magnetization in the xy plane. Now allow the magnetization to move, evolve for 270 degree, then what is going to happen? mx, my would be shifted by 270, then what is going to happen? And they will have a negative dispersion, other will be, you can understand what is going to happen. ms component will be negative dispersive and my component will be negative absorptive. This is what is going to happen. And This is what it is. When you move by 270 degree, ms component started here and went here and moved here. My component is here, started here and came down to here. It moved like this. The real part is dispersive and imaginary part is negative absorptive. This is what happens, and these points are very important for us to understand. After 360 degree, what will happen? Both the components will undergo one full rotation, and again it will come back, and then we will have the real part as positive absorptive and imaginary part as dispersive, because one rotation has completely gone through like this. Now this is after 360 degree pulse. This is what is important. Now I just applied only one RF pulse. I am collecting the signal as a function of time, allowing the magnetization to move with time to different axis. It moved to different axis. When I collect the signal, you will get different time. When you collect the signal, you have different phases: positive absorptive, negative absorptive, dispersive, negative dispersive. All you can come across. The same thing, what happens with the negative, if the magnetization is made to rotate counterclockwise. In this case, magnetization is made to move clockwise. If it allowed to move anti-clockwise, what will happen? Then 90 degree at 270 degree, the real and imaginary part will get reversed. That's all. Whereas for 0 degree and 360 it remains same. That won't affect. Whereas 270 and 90, the real and imaginary gets interchanged. That's all. If you make it to rotate in the opposite direction. No, otherwise there is no effect at all. This is what it is. So 0 and 360 will not get changed, it has no effect. 90 and 270 degrees, real and imaginary get interchanged if you allow the magnetization rotate in a counterclockwise direction. Clear? Now you can even calculate how much of the magnetization has been rotated during the delay that we have given. For example, I applied a 90 degree pulse, bring the magnetization component here, mx is here, and then after some time my is here, start rotating mx and my like this. Let us say after a time t, magnetization is moved like this. How much it has moved? If I give a time t, what is the amount of magnetization it has moved? What is the degree by which it has moved? We can calculate. It is not difficult at all. One can do the calculation. This is given by a simple formula called 360 into nu naught minus nu r into t. Nu naught is the frequency, it is the center of the spectrum, and nu r is the reference frequency. I am sorry, nu naught is the resonance frequency of the signal, nu r is the reference frequency, and t is the duration. This is what you have to understand. For example, this is my nu naught, nu r, I am sorry, nu r, it is the reference frequency is the center, and this is my resonating frequency nu naught. Then you have to calculate what is the frequency separation here. This is nu naught minus nu r, and then put this into this equation 360 nu naught into nu naught minus nu r into t. You will find out, if you know the t, how much it has moved, or if you know 90 degree, you can find out how much time it requires to move by 90 degree, how much delay you have to give, how much time you have to wait for the magnetization component to move by 90 degree or 180 degree or 270 degree. You can find out. Okay. So let us take the example like this is what it is. This is the center of the spectrum, reference nu 0, and then if I have a peak here and I have a peak to the right side of this reference or to the left side of the reference. Here nu naught minus nu r is what? Nu naught minus nu r is positive. Here nu naught minus nu r is negative. That is a convention. Remember, here when you come this side, this is going to be positive, this is going to be negative. That means the total rotation will be positive, counterclockwise viewed from the top. I view from the top of the z axis, it goes in the counterclockwise. This is positive, magnetization start rotating counterclockwise. Whereas if there is a peak here, it is negative, nu naught minus nu r, it's from the view from the top, it rotates clockwise from the top of the z axis. Let us say this is the z axis, view from the top, it starts moving like this. If I have a peak here, it moves like that. If I have a peak here, it moves like this. This is the convention you must understand. How much time it rotates for different degrees, how much for a different duration time can be calculated now. Now the direction of rotation of the magnetization we will try to calculate from this. Okay. Let us say I have a peak at 75 hertz downfield of the center of the spectral window. Understand my this thing very clearly. I have a peak at 75 hertz downfield of the center of the NMR spectral window. How much delay is required to rotate the magnetization by 90 degree? This is my question. Now I know what is the 75 hertz from my this thing. This is nu naught, and this is the this is nu r if you call reference. This is the nu naught. This is exactly 75 hertz from the reference center. Now this is what the spectrum is. My job is to find out what is how much is the signal which has moved. You can understand by this equation. All you have to do is to plug in the values for this equation. Nu naught minus nu r is 75. It is toward this side. Okay. Now put it here. 360 into 75 into t is 90 degree. I will say because I have to find out how much time delay, how much t is required to see that magnetization is moved from z axis to x or y 90 degrees. So this for signal to move by 90 degree. Now what I do is I calculate this thing, plugging this equation, all the values into this equation. It is 90 divided by this value. Now it calculate this one. It in the expressed in this thing it is 0.00333 seconds or 3.333 millisecond. If I apply a radio frequency pulse, if I have a signal at 75 hertz with respect to the center, now I wait for 3.3333 millisecond. The signal exactly moves by 90 degree with respect to the reference signal if I take it as nu naught. Okay. The magnetization will move from x axis to y axis with this delay because it moved by 90 degree. If the peak is absorptive, it will become dispersive. Fantastic, right? I can make the magnetization to become absorptive or dispersive just by allowing it to rotate for a period t after bringing it to the x axis or y axis. How much time I have to wait to see that the signal moves for 90 degree or 180 degree, I can calculate by this equation. Let us consider another simple example. I have NMR peak at 250 hertz upfield of the center of the spectral window. Upfield of the spectral window. How much delay is required to rotate the magnetization by 180 degree? Now upfield means I have to now take the difference. Nu naught minus nu r is negative 250 hertz. Now multiply by 360 into nu naught minus nu r into t. Now this has to be 180 degree. This is my condition. I want to see that magnetization rotates by 180 degree. Plug it in this equation. Nu r minus nu r is 250 that I know, which is given, and calculate t. T turns out to be 2 milliseconds. Simple equation. These are the numbers I have plugged in. I get 2 milliseconds. That means if I apply a radio frequency pulse, bring the magnetization to some axis. If I have a peak at 250 hertz, wait for some time. How much time? 2 milliseconds. Then this magnetization will move by 180 degree. That means signal which is positive absorptive will become negative absorptive. That is what happens. You can move this signal has moved by itself without doing anything. So these are the things which you should understand. With this idea, now we will understand the evolution of magnetization under scalar coupling. This is the evolution under chemical shift, because you are not doing anything, we keep moving it because of the offset, which nu naught minus nu r offset is also called chemical shifts. It is moving under influence of chemical shift. Now the evolution of magnetization under scalar couplings. I will take the example of a proton coupled CaCl3. What is a proton coupled CaCl3 carbon 13 spectrum? When it is coupled to proton, it is going to be a doublet with a JCH separation, which is about 210 hertz. Now consider on resonance. On resonance means at the center of the doublet. Okay. At the then delta nu is equal to 0. On resonance means there is exactly at the center frequency of the spectral width. So now this is the spectral width. This is exactly at the center. Now exactly on the on resonance double at the center of the doublet, I will take delta nu equal to 0. The two components of 36 doublets are like this. This is plus j by 2 and this is minus j by 2 from the center. And this corresponds to alpha peak, this corresponds to beta peak. We know that. Okay. So at t is equal to 0, I wait for some time, apply a 90 degree pulse, wait for certain time and start collecting the signal. You will see what is going to happen now. Now two components of doublet I have taken. CH doublet means one is j by 2, other is from the center, One is at j by 2, other is at minus j by 2. One is alpha peak, other is a beta peak. You know what is minus j by 2 and what is plus j by 2. And now magnetization initially will be like this. At exactly when you apply a delay and start collecting this signal, in my condition if I say t is equal to exactly 0, what is going to happen? When you start collecting the signal, both the signal will be in phase, and from the center they are separated by j by 2. This is called in phase doublets. Both the signals are in phase. It is a j split doublets, splitting because of the j coupling. Okay. So this is going to be j split doublet, both are in phase. Okay. Now I will do one thing. What happens if I collect the FID not at t is equal to 0, at t is equal to 1 over 2j and 1 over j. Two collections I will do. At 1 over 2j, what happens? The alpha and beta composite doublet will be out of phase by 90 degree. They move out exactly at 1 over 2j, they will be at like this, out of phase by 90 degrees. One is like this, other is like this. This is anti-phase magnetization. Alpha component would be positive and beta component would be negative. See, it will be, they are all moving in opposite direction. If both were like this, one moves like this, one moves like this. Okay. At 1 over j by 2, now alpha component is positive, beta component is negative. I did not do anything. I allow the free induction decay to evolve for some time. The time is equal to 1 over 2j, in which case we see that the doublet component, one has positive intensity, other has negative intensity. This is called anti-phase doublet. Remember, this is called here previous one we got in phase doublet. Both are in phase, both are positive. Here one is positive, other is negative. This is called in phase anti-phase doublet. Okay. So now at 1 over j, what will happen? Allow the magnetization to continue further. Alpha and beta composite doublet would be again in phase. But what happens? From here it started moving like this. From here this started moving like this. Both of them have moved, and they give rise to peaks which are negative absorption like this. This is what is called in phase negative absorption. This is a doublet component, in phase negative absorption. At 3 by 2, alpha and beta composite doublet continue to precess in opposite direction and will be out of phase by 90 degree. And this is anti-phase magnetization. Again, alpha component would be negative absorptive and beta component will be positive absorption. And exactly at 1 over 2j, now both alpha and beta component would undergo full rotation and come back and give us to positive absorptive signal. You understand now clearly. First we got the in phase, then we start moving, we will get anti-phase, then both will be in phase doublet. Then what is going to happen is this is going to be in phase negative, this is going to be positive. So this is again anti-phase. Finally, after 360 rotation, it will be completely, they both will come back and you are going to get absorptive, both absorptive signal, positive absorptive signal. Start with positive absorptive, anti-phase, negative, both of them anti-phase components, and then negative absorption, and then again come back. So this is what we are going to see as you give the delay, which is equal to 1 over 2j, 1 over j, 3 by 2j and 1 over 2j, 2 by j. If you give the entire doublet split, j split doublet components will be in phase absorptive, anti-phase dispersive, and then again it is going to become negative absorptive, both of them in phase negative absorptive, and then completely come back after one full rotation. So now there is some confusion here. What is the difference between absorptive and dispersive, you may ask me. And we are talking about in phase and anti-phase also. What is absorptive dispersive? What is in phase anti-phase? What is the confusion we have created here? Look at this one. Absorptive and dispersive line shapes are characteristic of a single frequency, only one frequency line. I collect in the along mx, along mx if the receiver is here, this is absorptive and this is dispersive, they are exactly out of phase by 90 degree. It corresponds to a single peak. They differ by signal. I can make this absorptive, I can make this this absorptive and this imaginary dispersive. Either way I can do. I can do the phase correction. Exactly I have to do phase correction. I may move this here and this here. I can make it imaginary as real, real as imaginary just by changing the phase. It is possible. So, in the case of absorptive and dispersive, phase correction is possible. You can make absorptive dispersive or dispersive absorptive. But in the case of the J-split doublet, both in phase and anti phase relate to the two components of the J-split doublet. It is because it is splitting with J splitting with carbon and proton. That is what we are considering CaCl3. Now, anti-phase spectrum cannot be phase corrected to make them appear as in-phase multiplets. Impossible. If it is anti-phase like this, you cannot make them in phase. If you try to make this phase, this will go down. Whereas absorptive and dispersive, you can make interchange them. You can make the phase correction, interchange them, but here it is not possible. This is one important point you should remember. Absorptive and in phase and anti phase are the multiplets. In case of doublets, they are J split components. You cannot phase correct them to make it either absorptive, positive absorptive or negative absorptive. Okay. So, you can also get both in phase, anti phase, absorptive and dispersive. This is a combination of both is possible. Very interesting. If I take some signal, I can get in phase and anti phase signal. This can be both absorptive and dispersive. Without going more into detail, I tell you. Now the signal is like this. This is called in phase absorptive. Both are in phase. And both are like this 90 degree. This is in phase dispersive. And they are like, both are like this. This is anti phase absorptive. See, both signal are opposite like this. Now if they are like this, signal are like this, this is anti phase dispersive. This is just J component, J split doublet I am talking. Just both the components of the doublet, if they are like this is in phase absorptive, this is in phase dispersive, this is anti phase absorptive, this is anti phase dispersive. Anti phase dispersive and in phase dispersive, you can see this goes like this, anti phase goes like this, whereas anti phase dispersive it goes like this. That is the difference. So, it is possible to get combination of both in phase, anti phase, absorptive, dispersive signal. With this, now try to understand what is chemical shift evolution and J coupling evolution. Delta and J evolution is very important. When the magnetization in the XY plane, both delta and J coupling will evolve, because both are, if both interactions are present, both will go. Now, if I consider the on resonance condition, the chemical shift do not evolve exactly on resonance. Chemical shift, that means nu naught minus nu r difference is 0. Then chemical shift do not evolve and only J coupling evolution takes place. For off resonance, that means nu naught minus nu r is not equal to 0. It is greater than 0 or less than 0, some other value. For off resonance condition, both chemical shifts and J couplings do evolve. This is an important point. Please remember, delta and J evolution takes place after application of the pulse by bringing the magnetization to XY plane. For on resonance condition, chemical shift do not evolve, only J couplings evolve, but off resonance condition, both chemical shift and J couplings do evolve. This is the point. Now, evolution of the chemical shifts multiplets, we should see how they evolve. We call this as a doublet. We have alpha and beta components. We have a triplet. We have alpha alpha beta beta component and alpha beta beta alpha components. And we have a quartet. This is alpha alpha alpha, this is beta beta beta. This is a combination of alpha alpha beta, this is alpha beta beta. There are 3 such possibilities here, 3 such possibilities. It is a quartet, it is a triplet. Now, how do these multiplets evolve? Always chemical shift at the center for the doublet and a quartet. For a triplet, chemical shift is the central component of the triplet. Now, let us see how they evolve. On resonance evolution of chemical shift, exactly when you are on resonance, I look for the chemical shift multiplets doublet, it will be exactly at the center. Now, if I take the triplet, exactly the component of the triplet. If I take the quartet, exactly center of the quartet. This is on resonance, chemical shift do not evolve. Okay. Now, of course, what happened to these components you may talk. I will show you when we go to J coupling. This J coupling do evolve in on resonance, that is what I said. They will evolve. But only for chemical shift to show, I am telling you, when you are on resonance, center of the doublet, there is no peak there. As I am telling you, center of the doublet is a chemical shift. That is how it evolves. Similarly, this is the central component of the triplet, this is the center of the quartet. How do they evolve? So, for a singlet, evolution is nothing but the frequency position. If I consider a singlet, chemical shift during off resonance I am considering, not on resonance. How does the chemical shift evolve? Single frequency, wherever it is, that is the chemical shift position. And for doublet and quartet, the chemical shift positions are the centers, center of doublet and center of quartet. For a triplet, it is the central component of the triplet, that is important. So, how the chemical shift evolution takes place during off resonance? Singlet is nothing but the chemical shift position of the singlet. For the doublet and quartet, it is the center of the doublet and quartet. For a triplet, it is the central component of the triplet. That these are the things which evolve. Now, diagrammatically we can see how they evolve. In the off resonance condition, the chemical shift evolution of a doublet and triplet and quartet, let us see. This is a doublet. Now we are talking about off resonance. Where is the chemical shift? Let us say one common component of the triplet, alpha is here, beta is here, let us say. Alpha, beta is here. It is a doublet. Two components are there. Where is the chemical shift now? There is no peak. There is no magnetization vector at that place. But you should understand the chemical shift here evolves at the center. Okay. Similarly, now the triplet, if I consider, they have evolved like this, alpha, beta. This is alpha, beta, beta, alpha. Now the center is here. Chemical shift of this is evolved like this. If I consider the quartet, doublet is here, doublet is here. Where is the chemical shift? Exactly at the center here, center of this. So, this is the chemical shift evolution, this is the doublet center, this is the central component of the triplet, whereas this one again at the center of the quartets. This is hypothetically there is no peak, but you have to understand how the chemical shift is varying. You can even calculate the frequencies, everything later. Now, we will talk about evolutions of the coupling. Evolution of the, how does the couplings do evolve? That also evolves on resonance and off resonance condition we have to consider. So, what we will do is, I think my time is up. What I will do is, I will stop here. We will come back in the next class. I will discuss about the evolution of the couplings, and then I will introduce to you more about polarization transfer, how the polarization transfer takes place between the antiphase components of the coupled spins, and more of other things we will discuss, product operator, various things we will discuss, NOU, MQT, etc. But today what you understood is evolution of the magnetization, how magnetization evolves under the influence of chemical shifts, when it is on resonance, when it is off resonance. When it is on resonance, if it is a singlet, in the on resonance, chemical shift do not evolve at all, but couplings will evolve. In the off resonance, chemical shift will evolve and couplings also will evolve. In the on resonance condition, in the off, okay, go to the on off resonance condition, if I consider a doublet, center of the doublet is the chemical shift, but there is no peak there, but you can imagine where the, imagine the direction where it is moving. So, you can find out the axis at which evolution of the chemical shift has taken place. Whereas, in the case of off resonance, triplet, center component of the triplet tells me about evolution of J coupling, I am sorry, evolution of chemical shift. Whereas, if I go to the quartet, central peak, central point of the quartet is the chemical shift. That tells me where chemical shift has evolved, if I have to find out the center of this quartet. So, off resonance, chemical shift do evolve, on resonance, chemical shift do not evolve. In on resonance, J couplings evolve, in off resonance, J couplings evolve. This is what you should understand. Now, the evolution of J coupling, how to take place, we will discuss in the next class. So, I will stop here. Thank you.